Hi, everybody. It's Professor Mitchell, and we're continuing with Chapter 12. Today, we're looking at Section 12.3, Exponential Functions. So we finally reached exponential and logarithmic functions, which is the title of this chapter. It's just that for the last two sections, we've been doing some background. All right, so we have previously worked with exponential expressions where the exponent was a rational number. So think x to the second, x to the fifth, or even x to the 1/2, or x to the negative 3/4. So what all of those expressions have in common is that the base is the variable and the exponent is a constant. So now we're going to turn it around and we're going to define the expression b to the x, where b is going to be a constant and x is going to be the variable. And you can define this expression for all real numbers x, including irrational numbers. And to go into the details of that, we would need a little bit of calculus, so I'll spare you that for now. All right, so a function of the form f of x equals b to the x is called an exponential function if b is greater than 0 and does not equal 1. All right, and remember that x can be any real number. So the only restriction is that the base has to be positive and it can't equal 1. We can graph exponential functions of the form f of x equals 3 to the x, g of x equals 5 to the x, or h of x equals 1/2 to the x by substituting in values for x and finding the corresponding function values to get ordered pairs. So the same way that we always graph a function when we see it for the first time. And when we do that, we would find that all graphs satisfy the following properties. They are all one-to-one functions. Remember, we talked about those in the last section. They would all have a y-intercept of 0, 1, and the reason for that is that any number to the power 0 equals 1. All right, you'll see an example of that coming up here. These graphs have no x-intercept. All right, there is no solution to an equation like 3 to the x equals 0. And the domain is all real numbers. Remember, in the definition, we said that x could be any real number. And the range of these functions are all 0, infinity. In other words, all positive numbers. All right, so ignore those little fractions there. That's just a malfunction with my animations. We're going to graph the exponential functions f of x equals 2 to the x and g of x equals 4 to the x on the same set of axes. All right, so might be a good idea to pause the video and think about how I got these values for f of x. The values for x, I just picked a few nice numbers, 0, 1, 2, 3, and then I threw a couple negatives in there. So where the f of x numbers come from is, for example, 2 to the 0 equals 1, like I was just talking about it a second ago. 2 to the 1 equals 2, 2 to the second equals 4, 2 to the third equals 8. And then remember how your negative exponents work. 2 to the negative 1 is the reciprocal of 2 to the first, so that would come out to 1/2. And 2 to the negative 2 is the reciprocal of 2 squared, so that would come out to 1/4. And then it's very similar for g of x equals 4 to the x. So I won't talk you through that same kind of explanation again. And if you were to graph these two functions on the same set of axes, you would get something like this. So the graph that is further to the right here is the graph of f of x equals 2 to the x. And then this one here is the graph of, that should say, g of x equals 4 to the x. So notice that both graphs pass through the point 0, 1. And to the right of the point 0, 1, the graph of g of x is steeper than the graph of f of x, and that's because the y values on the g of x graph are increasing much faster. Now, on the other side of the 0.01. It's just the opposite. The graph of g of x is flatter than the graph of f of x. All right, and now we'll do the same kind of thing for y equals 1/2 to the x and y equals 1/4 to the x. All right, so just briefly, 1/2 to the power 0 is 1. 1/2 to the power 1, I've got a bird serenading me in the background, is 1/2. 1/2 squared is 1/4. 1/2 to the third is 1/8. 1/2 to the -1 is the reciprocal of 1/2, which is 2. And 1/2 to the -2 is the reciprocal of 1/2 squared. 1/2 squared is 1/4, so the reciprocal of 1/4 is 4. All right, so when you graph those two functions, you get the graphs that you see here. Notice that these graphs are the mirror image of the two graphs that we looked at earlier. They've been flipped sideways, and there is a good reason for that. We don't talk about horizontal reflections in this class, but when you take pre-calc, you'll learn about horizontal reflections, and hopefully you'll understand then why these graphs are the mirror images of the ones we looked at before. All right, so it turns out, and this is really good news, that whenever you graph a function of the form f of x equals b to the x, the graph is going to look something like this as long as b, the base, is greater than 1. So that's like the first two examples we looked at. And if the base is between 0 and 1, like the second two examples we looked at, then the graph is going to look something like this. All right, now think back to chapter 8 when we talked about horizontal shifts. We would find a pattern in the graphs of all exponential functions of the type b to the x minus h, where b is greater than 1. Remember from chapter 8, when you replace x with x minus h, it shifts the graph h units to the right, all right? Okay, and then I had to fix a typo in this example that I had never noticed before. Now let's say that your base is between 0 and 1, just because, and you replaced x with x plus h. That would shift the graph h units to the left, all right? And of course, you can also shift this kind of graph h units to the right, or you could shift this kind of graph h units to the left. So these are just a couple of examples. All right, so when you graph this type of function, you have two options. Now I just noticed something here. Hold on one second. All right, I just noticed a couple of typos there that I had to fix. So in this problem, we're graphing the exponential function f of x equals 2 to the power x plus 2. So you have two options for graphing this function, and I find it kind of interesting that they chose this one to show you. So they just did it the same way that we did it earlier by making the table. So there's really nothing special about the numbers 0, 1, 2, -1, -2, -3. And when you plug those numbers in, you get these corresponding values for y. And when you plot these points, you get a graph that looks like this. So I just want to point out to you, this may not look great, but I want to point out to you that this is just the graph of y equals 2 to the x, which we looked at earlier. Sorry, hold on. I started talking for too long before I turned my pen on. Okay, so hold on, we'll get this. Oh, I know what I forgot to do. Okay, so the graph of y equals 2 to the x looks something like this, and this is actually turning out a lot better than I thought it would. All right, so if you take the red graph and shift it 2 units to the left, you get the graph that we're looking at. So that would be another way to do it, is just take the graph of f of x equals 2 to the x, which we had already drawn, and then shift it 2 units to the left. All right, uniqueness of b to the x. This is also called a one-to-one property. And you're going to see in just a second here how we're going to use this to solve equations. So the uniqueness of b to the x property says that if b is greater than 0 and does not equal 1, so that's just your usual requirement for the base of an exponential function, then if b to the x equals b to the y, we can say that x equals y. So let me show you now how we're going to use that property. In this example, we're going to solve each equation for x. First, we have 6 to the x equals 36, and then 9 to the power 2x plus 1 equals 81, and then finally 1/27 equals 3 to the 2x. So starting with letter A, we have 6 to the x equals 36. So what we're going to do first is rewrite 36 as a power of 6. And of course, that's 6 squared. So what this uniqueness of b to the x property says is that if 6 to the x equals 6 squared, the only way that can happen is if x equals 2. All right? So you just rewrite your two exponential expressions on the left and the right sides so that they have the same base. And then you can say that those two exponents are equal. All right. And as usual, at any point, if you want to try a problem ahead of me, I always encourage that. Just pause the video and then come back and compare notes. So for letter B, we have 9 to the power 2x plus 1 equals 81. So we're going to rewrite 81 as the power of 9. Of course, that's 9 squared. And by uniqueness of b to the x, if 9 to the power 2x plus 1 equals 9 squared, the only way that can happen is if 2x plus 1 equals 2. All right, so remember you have to solve this for x. We're not quite done yet, but that's just a baby linear equation right there. You can solve that in your sleep. If 2x plus 1 equals 2, then subtract 1 from both sides and you get 2x equals 1. Divide both sides by 2, you get x equals 1/2. All right, and that brings us to 1/27 equals 3 to the 2x. All right, so now how do you rewrite 1/27 as a power of 3? And if you're not quite sure off the top of your head, think about how do you write 27 as a power of 3? 27 is 3 to the 3rd, isn't it? And since 27 is 3 to the 3rd, and 1/27 is the reciprocal of 27, that means that 1/27 is 3 to the negative 3. So by uniqueness of b to the x, if 3 to the negative 3 equals 3 to the 2x, that can only mean that negative 3 equals 2x, which means x equals negative 3/2. All right, so that brings us to this slightly more complicated example. So what makes this example a little more complicated, and I love this kind of problem, by the way, 4 to the 3x minus 6 equals 32 to the 2x. If you start thinking about how to write 32 as a power of 4, which would be the logical first step, well, you might have trouble figuring that out, right? Because 4 to the first is 4, 4 to the second is 16, but then 4 to the third is 64. We skip right over 32. So whenever you find yourself in this situation where you can't write one number as a power of the other number, see if you can write both numbers as a power of some third number that you don't see here. And in this case, it would be 2, right? Because you can write 4 as a power of 2, and you can write 32 as a power of 2. 4 is 2 squared. 32 is 2 to the 5th. So we have 2 squared to the power 3x minus 6 equals 2 to the 5th to the power 2x. And then by properties of exponents, 5 times 2x is 10x, and 2 times 3x minus 6 is 6x minus 12. And now by uniqueness of b to the x, we can say that if 2 to the 6x minus 12 equals 2 to the power 10x, that can only mean that 6x minus 12 equals 10x. So now we'll subtract 6x from both sides, which gives us negative 12 equals 4x. And then divide both sides by 4, you get x equals negative 3. All right, and that brings us to some applications of exponential functions. Many applications use exponential functions of various types. Compound interest formulas are exponential functions used to determine the amount of money accumulated or borrowed. All right, so for example, let's find the total amount in a savings account if $5,000 was invested and earned 6% interest compounded monthly for 18 years. So this is like a couple has a new baby and they start a college fund, okay? And we're going to round our answer to 2 decimal places. That's usually what we do with money. The formula that is used for calculating compound interest is the one that you see here. A equals P times 1 plus R over N to the power N times T. And by the way, you will always be given this formula whenever you need it. Okay. So P is the initial principal invested. R is the interest rate. N is the number of times interest is compounded each year. And T is the time of the investment in years. And A is the amount of money in the account. So this is a real alphabet soup formula. Lots of different letters here. Okay, so in this case, $5,000 was the amount invested. So that's P. 6% is the interest rate. Notice that you have to write it as a decimal, so it would be 0.06. If you forget to write it as a decimal, you will usually get a really crazy answer. All right, so that'll tell you that something's wrong. N is 12 because we're compounding interest monthly. So that means 12 times a year. And T is the amount of time for the investment. So that's 18 years. So that gives us 5,000 times 1 plus 0.06 over 12. And that whole thing to the power 12 times 18. All right, so first we do 0.06 divided by 12, which is 0.005. And at the same time, we can do 12 times 16, which is 216. Then we do 1 plus 0.005, which is 1.005. Now at this point, you're going to need your scientific calculator because you need the scientific calculator to tell you what is 1.005 to the power 216. I would not want to try to do that by hand. And then after you multiply that number by 5,000, you get that the amount in the account after 18 years is $14,683.83. All right, here's another example. This is an example of exponential decay. An accidental spill of 100 grams of radioactive material in a local stream has led to the presence of radioactive debris decaying at a rate of 5% each day. Find how much debris still remains after 30 days. So the formula that would be used for this problem is y equals a times 2.7 to the power negative RT. And if you're wondering where does the 2.7 come from, I will tell you later. Where A is the amount of radioactive material to start, R is the rate of decay, T is the number of days, and Y is the amount of radioactive material after the time period. So in this problem, we're trying to find Y, and we're given that A is 100, R is 0.05, and T is 30 because it's asking after 30 days. So first we do negative 0.05 times 30, and that comes out to negative 1.5. So they're pointing out to you that this would be your exact answer. But usually for word problems, we don't care about an exact answer unless it's a nice answer that everybody can understand. We're going to ask the calculator to approximate that answer. And it turns out that after 30 days, there would only be about 22.54 grams left. So that's less than 25% of what you started with. And that's going to do it for section 12.3. The next section will be 12.5. All right, we don't cover section 12.4. See you then.